In this example, we're going to approximate the integral of x squared from 7 to 8 using a Riemann sum with a delta of x of 0.05. To build this, we need two units. The first unit represents the function x squared, where the red point has an input value. The yellow point is fixed at 2 for the square, and the blue point gives the result of the function x squared. The second unit is set as a Riemann sum. The input here is going to be linked to the output of the first unit. So every time the function produces a new value, like this, that value is added to the running sum. So we link the two units like so. And then you have the result. The first unit has a delta value on its red point. We can set it like this, set delta value. In this case, we're going to set it as 0.05. This delta determines how much the value of x changes every time I turn the mouse wheel. In this example, I set it to 0.05, so the function will be evaluated at 7. 7, 0.5, 7.1, and so on until we reach 8. The Riemann sum unit also has a red point with its own value. This is also set as the same 0.05. These values should be the same. The first delta determines where the function is evaluated, while the second delta determines the width of each rectangle. If both are set to 0.05, the calculation follows the usual definition of a Riemann sum. So the fact that you can see these two delta values independently means you immediately see what happens when they differ. If the Riemann delta is larger than the steps used to evaluate the function, the final result will be too large. If it is too small, then if it's smaller here, then the result will be too small. So although you can choose different values, they no longer represent the standard definition of a Riemann sum. Now I'll set the red point of the first unit to 7. As I move from 7 to 8, the first unit continuously evaluates the function x squared, while the second unit accumulates each new function value. So every evaluation is recorded in the Riemann history, and you can see the running sum gradually approaches the approximation of the integral over the interval from 7 to 8. You should notice that I'm not simply entering the final value of h. The operation is built from many consecutive evaluations of the function, so the interval has to be spanned out from one step at a time. In other words, the approximation is constructed by walking through the interval instead of jumping directly from the beginning to the end. What happens if I reverse the direction with the mouse wheel? Like this, whenever I move backwards the mouse wheel, the last entry is removed from the Riemann sum, and the running sum returns to its previous value. You will also notice whenever you're using this operation that there isn't currently a way to specify the start and the end of the interval and have the entire integration calculated automatically. Instead, you move through the interval yourself, one delta at a time. So if I wanted a much more accurate approximation, using a very small delta like 0.005, or if I wanted to integrate over a much larger interval, the calculation would naturally take much longer because every intermediate point has to be evaluated individually. The intent here is that Visuali is primarily an educational platform rather than a calculation program. The goal here is not simply to obtain the numerical answer as quickly as possible, but to understand how the answer is built. By the time we reach 8, if we go from 7 to 8, the accumulated value represents the Riemann sum approximation of the integral of x squared over the interval from 7 to 8, using a step size of 0.05.